The objective of this lab is to study Kirchhoff's circuit laws. Circuit A on the left is to study Kirchhoff's voltage law. Circuit B on the right is to study Kirchhoff's current law. To complete a lab assignment, do every task in the lab report outline. There is one-to-one matching between the list of tasks and the lab guide app items. The function of an AC adapter is to take AC power input from the wall plug, and gives a DC power output for the appliance, such as a laptop. The input AC voltage varies as a sinusoidal function of time, alternating between positive and negative between the two terminals. The output of the adapter is a constant voltage, which is 19.5 volt in this particular case, and it doesn't change versus time. Take a look at the street pattern below. The arrows indicate one-way streets. An entering car can turn left or right. There is no street direction sign for block BC. Is BC traffic one-way, or two-way? Click play below to see. All incoming traffic must go through B and C, and always from B to C, even without an one-way street sign between B and C. The street traffic can be converted into an equivalent electrical circuit. The one-way street sign can be implemented with a diode or LED. The street pattern can then be converted into a circuit. Every one-way sign is implemented with a LED. In principle, there is no need for an LED between B and C, however, an LED is inserted in order to demonstrate the existence of one-way current flow. One can insert another LED with the opposite polarity, and that will remain dark, showing that the current flows only one way, just like the street pattern. The circuit has two more elements that aren't shown in the street pattern. The two resistors act as the speed limit signs. Just like high-speed traffic is not desirable, the resistors act to prevent high current flow. The analogy of car traffic and circuit current flows can be seen with synchronized side-by-side comparison. For both, the flow direction is always from B to C. Consider a similar bridge circuit structure, but all segments allow two-way flow. What is the flow between B and C? This is the second part of this lab. The previous circuit has what is known as a rectifier bridge, the bridge between two nodes, B and C. Here, we have a different bridge, known as the Wheatstone bridge. This is not about one-way flow, but about which way it flows. Consider two nodes of a circuit. If connected with a bridge, is there a current flow, and which way does it flow? Click the applet below for an illustration. Between two nodes of a circuit, such as B and C shown, if a passive device is connected between them, the current will flow from the high voltage node to the low voltage node. In the illustration below, the current, as represented by the ball, goes from B to C when B has a higher voltage than C. It reverses the direction when VC is higher than VB. It will stay in the middle, which means no current flow when B and C are equipotential. In the circuit to be built, two LEDs in the bidirectional configuration will be placed between nodes B and C. A LED of one color will light up to indicate the current flow of one way, and another one of a different color will light up to indicate the current of the opposite way. Both circuits above are to serve an objective of this lab, which is to study Kirchhoff's circuit laws. The rectifier bridge circuit is used to study Kirchhoff's voltage law. The Wheatstone bridge circuit is used to study the Kirchhoff's current law. How will that be done? The applet below is a sneak preview about applying Kirchhoff's voltage law to the rectifier bridge. Don't worry about the details for now, we will get into it later in part A. The important point here is the concept of using KCL and KVL to analyze and eventually design circuits. The follow is an illustration of how Kirchhoff's voltage law is applied to the rectifier circuit. Click the app icon, and an app window will pop up. This is a screenshot recording of using the app. Click step play or slide below to see the application of Kirchhoff's voltage law. Toggle for sound on off. Measure VAB. Measure VBC. Measure VCD. Measure VR2. Measure -V source. Adding all of them should give 0. Click button below for example calculation. There are 3 parts of this circuit. This part is the actual circuit of part A. It is slightly different from its basic version, because it is for the AC-DC conversion demonstration in step 5. There is another part, shown here, that is only for the demonstration and it is for bonus work and credit, if you work only at home with the DG Lent AD2, shown as the last part. If you do work in the lab, only the basic circuit is needed, and the function of the other 2 parts can be done with the lab signal generator. Please ask the teaching assistant for help if necessary. This video shows how the rectifier bridge circuit works. The LEDs are a bit too bright for the camera, a dark filter was used. When the polarity is one way, a set of LEDs light up indicating the current flow path. Reverse the polarity, and the current flows the other path, lighting up the other set of LEDs. The bridge LED in the center, however, always lights up. It means that while all other LEDs are active only on 1/2 a cycle of the sinusoidal AC voltage, the bridge LED is always on for the full cycle. Step 2 and Step 4 of this part A are to demonstrate what's shown here with the circuit you build. If something blinks really fast, it looks steady. This is a demonstration of how the AC-DC adapter works. If the input AC sinusoidal voltage varies slowly, although the bridge LED voltage is DC, it is still off when the voltage goes to low or 0. One way to maintain a constant DC is to let the AC vary very fast, along with a device that can store electricity like a backup battery. This device, as we will learn later, is known as the capacitor. Observe that when the blinking is as fast as the camera's sampling rate of 30 frames per second, the camera can no longer tell when the LED is off. In reality, only the bridge LED is truly steady, other LEDs still blink, but the recording camera cannot tell. This is known as Nyquist aliasing effect. The bottom line is, when the AC voltage oscillates fast enough and the electricity storage device is sufficiently large, the circuit gives a constant DC output, which is why it is called AC-DC adapter. Step 1. Build the rectifier circuit. There are many ways to build a circuit based on the schematic. Below is only an example. Whether building the circuit by your own design or using the step-by-step applet, always make a mental correspondence between a physical element, such as a wire, a resistor, a LED, with its representation in the schematic. This practice can help one to quickly get a hang of it and become an expert in short order. Put in resistors R1 and R2. Put in pairs of input LEDs. Put in bridge LED. Put in pairs of output LEDs. Put in return wires and the rectifier circuit is completed. You can exit or move on to see locations of the nodes for future measurements. This is node A. This is node B. This is node C. This is node D. This is node C. This is node B. This is node A. The rectifier circuit is completed. Take out return wires. Take out pairs of output LEDs. Take out bridge LED. Take out pairs of input LEDs. Take out resistors R1 and R2. Put in resistors R1 and R2. Put in pairs of input LEDs. Put in bridge LED. Put in pairs of output LEDs. Put in return wires and the rectifier circuit is completed. You can exit or move on to see locations of the nodes for future measurements. This is node A. This is node B. This is node C. This is node D. This is an example of a circuit built, top view. This is a side view. There are two options for the voltage source. If you are at home, you are strongly encouraged to use the AD2 voltage source outputs. In the lab, you can use either the AD2 or the BK precision power supply. For this particular picture, the V+ and V- wires are from the AD2. Step 2 is to turn on and test the circuit. Feel free to explore and learn by trial and error. If you wish to apply what learned in other circuit analysis courses, this app provides a simulation, and one can get a feel for the circuit. Notice that we use the ideal diode model with zero reverse bias current. The circuits have two distinct meshes for the two voltage polarities. The app calculates the voltages, currents, and powers in the devices. Configure the app circuit to match the actual LEDs and resistors of your circuits. The built-in LED calibrations of this app may be different from your LEDs. You can obtain your own LED IV curve calibrations and insert them into the app. But it is not that important, because no exact or specific value of the current or voltage is needed. Just keep the current within the suggested range. Observe the table of device voltages. This is what will be measured in step 3 and step 4 next for Kirchhoff's voltage law. The most relevant thing is how to control the voltage. Observe how the current is sensitive to the voltage in certain range. You can do fine voltage control with the AD2 cursor. In the lab, if you use the BK precision power supply, use coarse voltage control up to a level slightly below what needed, then use the fine control knob to tune. You can choose any resistance value between 100 and 200 ohm, higher value to limit the current. Exploring, tinkering the circuit is a part of learning. Put in different resistors to observe the change. A fundamental consideration in circuit design is the device power. The bar charts allow one to monitor the device powers within a design range. This is an example. One set of 3 LEDs light up for one polarity, and another set light up for the other polarity. Switching polarity can be done manually by physically swapping the two voltage supply wires. In this particular case, the wires are from the AD2 voltage source outputs. Common to both sets of LEDs is the bridge LED in the center. It is always on. No matter what polarity, as expected. This step involves the measurements of the voltages of each element in a mesh to study Kirchhoff's voltage law. In Lab 1, and for the most parts of this course, the home-based handheld multimeter is usually good enough. In this particular case, it is more educational to use a more accurate and higher precision instrument, such as the AD2 or the lab multimeter. If you have no alternative, it's okay to use the handheld multimeter. This is the basic idea of verifying Kirchhoff's voltage law with the circuit. Skip if you feel you are already familiar with it. This app shall guide through the measurements for Kirchhoff's voltage law. Follow instruction for each step. Enter the data into the input box, it will save your data and at the end, will compute the figure of merit of KVL applied to the measurements. Toggle for sound option. Click Start when you are ready. Measure VR1. Markers off. Markers on. On the breadboard, there are two markers, an orange black ring and a blue black ring. Put two wires into the breadboard holes indicated by the orange and blue markers. Clip the hook or alligator connectors of the voltmeter test leads to the other ends of the wire. Orange marks the plus polarity. This scheme uses the leapfrog approach. The end point of one segment is the start point of the next, and it forms a physically close loop on the breadboard. Measure VAB. Measure VBC. Measure VCD. Measure VR2. Measure -V source. When a red calculate button appears, click it and the result will be shown. You can click Save Data then clear to do a new measurement, or just clear without. After the LED rectifier circuit is built, one should do a measurement to verify Kirchhoff voltage law, which involves the measurements of voltages across the segments of a mesh. For the illustration purpose, a wire has been inserted into each node location of the segments and tagged with numbers from 1 to 6 as shown. The wires will be connected to the AD2 scope channel 1 for voltage measurement. The bottom image shows the app that one can use to do measurements in Part A, Step 3. The app shows two markers across resistor R1. They correspond to the two wires with tags N1 and 2 in the top figure. Please click Next. Now, the circuit is turned on, ready to be measured. To measure the voltage between 1 and 2, which is VR1 in the circuit, we connect the two wires from AD2 scope channel 1. The plus terminal is connected to wire 1 and the other to wire 2. Hence, the voltage polarity reference will be from marker 1 to marker 2. Once the scope terminals are connected, we can read the AD2 logger to see the voltage. Here, we choose to read the mean value of the data that are continuously measured for every 200 millisecond. Then, enter the measurement value into the app as shown. Here, the value was 0.7941 volt. Given R1 is 100 ohm, it implies the current was 7.94 milliamp. After measuring VR1, we can move the scope terminal that was on wire 1 to wire 3, while leaving wire 2 alone. This simply reduces the plug and unplug action that may accidentally cause wires to be touched, disconnected, or falling off. If we look at the measurement, because the polarity is reversed, we should minus whatever value and enter into the app. Keep on doing the same until the last step, which is to measure between marker 6 and the original marker 1. This is the minus voltage of V source because we measure from marker 6 to 1. Be sure to enter the negative value. Once the data is completed, the app will show a red button. Push to perform a calculation of the figure of merit of Kirchhoff's voltage law. This particular measurement shows that Kirchhoff's voltage law is held true to within 0.036%. You can save the data to be put in the lab report. For Part A, Step 4, it is about doing the same thing, but with reverse voltage. A few markers are the same, but a few are different, as indicated in the app of Step 4. Do the same thing as above for Kirchhoff's voltage law, but with the reverse voltage polarity. This is an example of swapping the source voltage wires, which are from the AD2 in this case, to reverse the polarity. The wires can be hot swap as long as they don't touch each other. Or, the AD2 voltage can be clicked to switch off during the swap to avoid accidental short. When turned back on after swapping, the voltage magnitude needs not be the same. Even if the source voltage magnitude is exactly the same but with an opposite sign, do not expect all the LEDs voltages will just flip the sign. No two LEDs even of the same type will have the same IV characteristics up to 4 digits. The numerical figures will be slightly different from those of the previous cases, and that is perfectly normal. There are two options. Option A, just observe a demonstration of Part A, Step 5, which is about how AC-DC adapter works. Or Option B, with bonus, to do some or all parts of the demonstration. At the minimum, Option A, no experimental work is required. However, any effort of doing hands-on work will be highly valued for Option B. You are encouraged to explore, tinker, and report of your hands-on work with as much details as possible for extra credits, which will be given generously. Use the signal generator to generate a square wave width at a frequency of 5 cycles per second or less. Increase the amplitude from 0 until you see the LEDs start blinking. Note that the bridge LED is steadily on, not blinking. Use your cell phone camera to record it while changing the frequency to around 30 cycles per second. Observe the strobing effect. Test your vision. At what frequency you cannot tell if the LEDs are blinking or not. Why do you think most TV and displays refresh at 30 frames per second, not 10 frames, not 100 frames? Do not search on the internet and write a paragraph about AC-DC adapter. Consider this analogy. There is a movie with a plot twist. Would you want to watch it to find out the plot twist yourself, or would you want to read someone else's review with spoilers? The objective here is for you to use your own circuit, tinkering and finding out firsthand by yourself how the rectifier works. However, since the extra amount of work is substantial for one lab assignment, it is good enough to observe the demonstrations, and figure it out. Can you tell which blinking behavior corresponds to which waveform? Observe the bridge LED. Sometimes, it is steady, sometimes it is not. The bridge LED is on constantly and steadily when the waveform is square. The AD2 was used to prove it. The blue straight line is the voltage across the LED measured by the AD2 as a function of time. It is constant like a DC voltage. The input is a square alternating voltage with half of the time being positive, and half being negative. This is a simplest example of AC-DC conversion. When the waveform is sinusoidal, the bridge LED is not steady, but blinking. The reason is that there are times when the voltage magnitude falls below certain level and all LEDs including the bridge LED are off. Even though the bridge LED can be on with both positive and negative half cycles, there are times when it drops below the threshold level and actual goes to zero as shown by its blue voltage curve. This is a rectification process, but not a perfect AC-DC conversion, because the output is not DC steady. In fact, the bridge LED current as represented by the yellow curve can be seen going to zero. These are off times of the bridge LED, when its voltage, the blue trace also drops below the turn-on value, which is also known as contact potential. As a side note, the reason why we cannot show this yellow LED current curve in the previous view is that the AD2 has only two voltage measurement channels. Previously, the yellow curve channel, scope 1, was used to show the input sinusoidal voltage. Here, that curve is used for the LED current. An interesting side note related to Lab 1 is that the XY plot function of the AD2 software can be used to display the bridge LED voltage on X-axis and the LED current on Y-axis, to yield the LED IV curve. The bottom line issue here is, the off time of the bridge LED is quite long in one cycle, causing it blinking instead of what is desired, which is a steady, constant voltage and current across bridge BC. There is a way to solve this problem. If the only water source comes from rains, it would be inconvenient to wait for rains when needed. A water tank can serve as a reservoir. For electricity, one type of reservoirs is the capacitor. A capacitor can store electricity when the voltage is high, like when there is rain, and release electricity for usage when the voltage is low, thus making electricity supply more steady, just like the water supply from a storage tank. Capacitors come in different sizes. You should have a few large ones in your kit, and at least one very large one as shown in the picture. The next step is put a capacitor in the circuit. To the original rectifier circuit, a capacitor is added parallelly with the bridge LED. That's all should be needed. However, it is slightly more involved because the AD2 signal generator does not have high enough voltage for the circuit. Hence, what is needed is an amplifier. Shown here is an amplifier that gives an output 10 times larger than the input. If you work in the lab, the signal generator on the workbench can give a large signal and the amplifier is not needed. If you at home and wish to do the demonstration, follow instructions given a bit later how to build the amplifier. Lastly, whether you are at home or in the lab, it is convenient to use the AD2 for data control and acquisition. Here is a suggested approach to use the AD2. 3 functions are used. 1 function of signal generator, and 2 functions of voltage measurements, also known as scopes. It has only 2 scope channels. Use a 6-pin connector, given in the kit, as a hardware interface between the AD2 and the circuit. The signal generator function is set to give a sinusoidal output. The signal is then amplified by the amplifier. The scope outputs are displayed on the screen by the AD2 waveform app software. Scope 1 gives the yellow trace on the screen. It is used to monitor the amplified signal that is input to the rectifier circuit. Scope 2 gives the blue trace on the screen. It is used to measure the voltage across node B and node C, which contains the bridge LED. It is straightforward to configure these functions of the AD2, and once done, it can be saved as a file, so that the next time it is opened, the AD2 will run exactly like when it was saved. A number of configuration files are shown here and available for download if interested. If you are at home, then the amplifier is needed. It is not wasted of effort, because this is what we will learn to do in Lab 4 later. Here, there is no need to know how it works. One can just duplicate exactly what is shown in the picture. 1 volt signal from the AD2 will be amplified to 10 volt signal that drives the rectifier circuit. Now, let's try with a 10 microfarad capacitor. First, the circuit was run with it, then it was removed. Is there any noticeable difference in the bridge LED behavior with and without it? It is not obvious if there is any difference. The scope traces of the AD2 show what happened. Without the capacitor, in the top graph, the bridge BC voltage drops to 0. In the bottom graph, the capacitor did its job as the voltage remains above 0. However, the voltage did not stay high enough to drive the LED, hence it still blinked off. Like a water tank that doesn't store enough water for usage after a rain, this means that bigger storage is needed. A large capacitor of 470 microfarad is now used. Observe the bridge LED behavior when the capacitor is connected, and when it is disconnected. Do you notice any difference? To see the difference, if any, we can also use the image data captured by the camera. A small area around the bridge LED image is selected and cropped. Then red-green-blue decomposition is applied. The integrated RGB light powers within the cropped image are plotted as a function of time as shown. Clearly, the camera's sensor can indeed see a difference when the capacitor is connected, and when it is not. This shows that the large 470 microfarad capacitor does work as expected. Note that the bridge LED is nominally green, and indeed, the green and blue light behaviors are different from that of red, which is likely composed of mostly light from the nearby red LEDs. The AD2 scope data also show the evidence. Compare with the small 10 microfarad on the left, the large 470 microfarad data on the right shows that the bridge BC voltage, shown as the blue trace, is indeed flatter with smaller ripple compared to the data of the small capacitor. Besides the size of the storage, does the frequency matter? If it rains often, the water storage should always be ample and the water fluctuation must be less, that is, the water supply is steadier. Same with electricity. This video shows the rectifier circuit behavior with the large capacitor for different frequencies from less than 1 frame per second to 60 frames per second. Note that the bridge LED blinks at low frequency, but becomes steadier at higher and higher frequency. Other LEDs are always blinking, but because of strobing effect, or Nyquist aliasing, when the LEDs blink at the camera frame rates of 30 frames per second, it doesn't look like blinking. Only the bridge LED is truly steady. What this shows is that the higher the input voltage frequency, the steadier is the bridge, which means that it is indeed DC-like. Data from the AD2 scopes also show the rectification behavior versus input voltage frequency. From low 2.5 Hz to 60 Hz, the output bridge voltage, the blue trace becomes flatter and flatter, and at 60 Hz, it is essentially DC. This is what this lab starts out. The function of an AC adapter is to take AC power input from the wall plug, and gives a DC power output for the appliance, such as a laptop. The input AC voltage varies as a sinusoidal function of time, alternating between positive and negative between the two terminals. The output of the adapter is a constant voltage, which is 19.5 volt in this particular case, and it doesn't change versus time. In this part A, we learn how the ubiquitous AC-DC adapter works with the simple rectifier circuit. Actually, there is one more element, the transformer that can change the voltage amplitude, but it is outside the scope of this course. Watch this video. As the signal rate changes, at some point the LEDs appear frozen in time. They are actually still blinking, but because the blinking is so close to the camera recording rate of 30 frames per second, or a multiple of it, which is 60 Hz, the camera cannot tell. An analogy is this. The key idea is that if we want to measure the time behavior of something, we must measure more frequently than the rate of change of that thing. So, A camera monitoring the dog every few minutes throughout the day will tell more than our impressions taken only twice a day. By corollary, it can be said that given a sampling rate, we can never know the change that happens faster than our sampling rate. This is more rigorously known as Nyquist's sampling rate theorem if you take a course in signal analysis. A simpler way of saying is that never assume that you know what happens during the time interval you are not looking. A similar idea is interpolation between two data points, say A and B. Any interpolation has inherent uncertainty. No circuit theoretical calculation is required in this lab course. The following are details of the various apps used, for the information purpose. There are two functions for LED calculations. The functions require specific LED parameters that are obtained from calibrations. As examples, these are calibrations for a batch of old 5mm LEDs. The newer 3mm high-efficiency LEDs are similar, and many are essentially blue LEDs. To calibrate the IV curve of a LED, the following is a suggested approach. Start with this simple circuit. Step 2, use a 6-pin connector that comes with the AD2 kit. If you don't have it, just use 6 short pieces of wires, each with one end inserted onto the breadboard, the other end sticking up like the connector. There are 2 short jumper wire connections. Step 3, locate the various cables from the AD2 connector that comes with the kit. There are 3 pairs of cables, signal 1, scope 1, and scope 2. Each pair has a plus and minus. Insert the cable ends onto the 6-pin connector gently, avoid bending or breaking the pins. There are some flexibility that you can interchange the cables if necessary. 1. Signal 2 can be used instead of signal 1. Then, the waveform programmed on the DG-Lens software control should be configured to output to signal 2. 2. The scopes 1 and 2 can switch places. 3. Even the plus and minus of each scope can be swapped, but the sign must be corrected after the data acquisition file is saved. 4. Do not swap the signal plus and minus, unless the sawtooth waveform programmed on the DG-Lens software control is changed of its polarity. On the AD2 control page, set up a sawtooth waveform, or sinusoidal, with positive polarity. After setting up the waveform, click Run and the AD2 signal 1 is sent to the circuit on the breadboard. Click the scope function, and the AD2 automatically and simultaneously measures, records the voltages across the resistor, which is scope 1, and the LED voltage, which is scope 2. Per Ohm's law, the resistance voltage is proportional to the LED current, and hence, the IV curve can be displayed by selecting the XY function of the AD2 scope control, as shown here. Adjust the waveform amplitude as needed to have the current up to 20 or 25 mA. Just click Save, select .csv format, and enter a file name. The measurement is completed. The saved data is input into a numerical model fit computer code to yield the LED model parameters. The model fit code written with Mathematica is available for download.